So this is the 1985 Mechanics 1 AP problem. In this problem, we have a projectile is being launched from the top of a cliff above ground level. So there's your cliff. At launch, the projectile is 35 meters above the base of the cliff and has a velocity of 50 meters per second at an angle of 37 degrees with the horizontal. So it's being launched from here, which is 35 meters above the ground, and with an angle of 37 degrees above the horizontal. Air resistance is negligible, and G is equal to 10 meters per second, and here's the path it travels. These parts will be important later.
Maybe.
Okay, so there's your picture. Question A asks for the total time from launch until the projectile hits the ground at point C, which is right here. Here's point C. And it asks for time. So we can use a Vividat equation here. VI, VF, DAT. And we can only use the y direction. Yes, the y direction will be necessary here. And acceleration in the y direction is 10 meters per second squared. That's just gravity. T is what we're solving for. It is 35 meters above the ground. So that is 35 meters. And it says, the question says that it has a velocity of 50 meters per second at the start at an angle of 37 degrees. So we can draw that vector here to get the y component. It's 37 degrees and it's 50 meters per second. So the sine of 37 degrees is 0.60 times the y here, or equals, yeah. So 0.6 times 50, that's just 3 meters per second. 30 meters per second, sorry.
Gosh darn it, Yandiel.
So we can say that this is 30 meters per second. And then we have everything we need to solve for t.
Not quite.
This. What?
Show them your positive direction.
Okay. Since positive and negatives are important here, we'll say that when the ball travels up is positive. Whenever it goes down, that'll be negative.
Okay.
Now we have everything we need.
And gravity is?
I already said that. Yes, gravity will be negative because the ball is going down. Now we have everything we need?
Yes.
We can use the equation D is equal to VI times T plus 1/2 AT squared. Plug in everything we have. We have 35 meters is equal to 30 meters per second times T plus negative 10 meters per second squared over 2 times T squared. Then we have just solve for T. That is now a minus 5 meters per second squared times T squared. Move that over. So we get 0 is equal to 30 minus 5.
That's 30t.
It is 30t, yes. Minus 5t squared. So you have your equation here and you're solving for t. You can either use your calculator, use the solver on your calculator, or you can use the quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over a squared.
2a.
2a. Not a squared, 2a. So you do that, and you get that t is equal to 7 seconds. And that is part A. Part B. Calculate the horizontal distance r that the projectile travels before it hits the ground. So r is here. To solve for r, first of all, time is the same in the y direction and the x direction, because it only falls at one time. That's not going to change. And velocity in the x direction we already have, as you can see in the triangle here, we got the y direction, got the whole vector, and now the x direction. This is a 3, 4, 5 triangle. So velocity in the x direction is 40 meters per second. And we can say that 40 meters per second times the time, which is 7 seconds, is equal to the distance. That's an s. You can see the s's cancel, and we're left with meters. So 40 times 7 is 280 meters. And that's B. C says, calculate the speed of the projectile at points A, B, and C. Here's A, here's B, and here's C. And it wants the velocity at those points. So the velocity at A, you can see here that at A, the ball is starting, like, instead of rising up, it's going to start falling there. Meaning that at that point A, there's no y
Velocity.
velocity, yes. So vy is 0 at point A. So we only have x. And there's no acceleration in the x direction. So x is going to be the same speed throughout this whole path. And x is just 40 meters per second at VA. And then at B, you can see that B lines up to where it was launched at, right here. So it's still at 35 meters here. And the problem says it launched 35 meters above the ground at 50 meters per second. And that's B. And then for C, we can use the kinetic energy equations, yeah. Because finally, at part C, kinetic energy is where is my work here? 1/2 V at C. Oh, I forgot the M. 1/2 mv at C will be equal to kinetic energy final is equal to kinetic energy initial. V squared. Yes, kinetic energy final is equal to the kinetic energy initial. And initially, kinetic energy was 1/2 mv squared plus the potential energy mgh. All the m's cancel, and v is equal to 50 meters per second. So we have 1/2 v squared to 1/2 v squared plus gh. Just plug in all you know and multiply by 2 to get rid of the half. So we got v is equal to the square root v squared plus 2gh. Plug in everything, we got 50 squared. Square root of 50 squared plus 2.
Is that VC
times,
equals?
Yes, that is VC equals 50 squared plus 2 times 10, which is gravity, times the height, which is 35 meters. And VC is equal to 56.6 meters per second. For part D, up here, there's another case. In this case, there is a small internal charge explodes at point B in the above diagram. Let me try that. Here's the part B where it explodes. And there are the two pieces. Causing the projectile to separate into two parts of masses 6 kilograms and 10 kilograms. The explosive force on each part is horizontal and in the plane of the trajectory. The 6 kilogram mass strikes the ground at point D. So here's point D. That's where the 6 kilogram mass strikes it at. Located 30 meters beyond point C, which is right here. This is where the ball would have landed if it stayed whole. And it lands 30 meters away from that. And then a 10 kilogram mass strikes the ground at point E, which is over here, at a distance x away from C. I would ask us to calculate the distance x from C to E. So we can use momentum, conservation of momentum. Say that V1, M1 is equal to V2, M2. we can call this our M2. And then over here is 10 kilograms. That's our M1. So time being the same allows us to use the
Momentum.
Use the momentum. Yeah, time being the same allows us to use the momentum equation. V1 M1 equals V2 M2, and V is just D over T, and we can replace that in and say that V1 is equal to the distance that the first piece traveled over the time times the mass of the first piece, and V2 is equal to the distance that the second piece traveled over time, which doesn't need a number because it's the same, times the mass of the second piece. And the times cancel, so we're just left with D1M1 equals D2M2. And D1 is what we're solving for, also known as X. We just plug in the equation, D1 times the mass of 1, which is 10, is equal to D2, which is 30, times the mass of the second one, which is 6. So multiply and divide, and we get that D1, or X, is equal to 18 meters.